Okay, so like I said, we're going to put Unit 3 at the top of this, and I'll post these lessons online here shortly when I get around to it here, but I'll give you some Google lessons and some PDF lessons, and I'll post the worksheets too, but we're not going to have any homework today, so. Yeah, okay. Very important definitions in this unit that we need to know, okay? You got to fill in some stuff here because you don't have all this. So just so you know, obviously we're going to talk about, if we're going to talk about solutions, we're going to talk a little bit about a solution is a mixture made up of a solvent and at least one solute. That solute could be anything. So, you know, for example, if you're going to take sugar and put it into water, sugar would be the solute, water would be the solvent, okay? Or salt into water, sodium chloride would be the solute or the solid, and water could be the solvent in that case. It doesn't have to be a solid. It could be another liquid that we decide to put into water, or any other liquid, or any other. It doesn't have to be water, by the way, but that's what we're going to focus on. But and it could also be a gas. So we could bubble in a gas, for example, and we're going to talk a little bit about that coming up with when we get to acids. So if you take a gas and you put it into water, that could be an example of a solute and solvent water. Okay. Next, solutes and solvents may be gases, liquids, or solids. Has everyone got that? We're going to do this exclusively. So again, aqueous solutions are where water is the solvent. That's what we're going to be all talking about in this unit. Water is going to be the solvent. Okay. Feel free to copy all this down here, eh?
You said it like once if you said it.
No, I don't think. Okay. All aqueous solutions are transparent or colorless. Transparent can be colored or colorless. So that means basically all aqueous solutions can be see-through, transparent, or they might have a color to them. Okay, so they might be a pretty blue or red or green or whatever, and they also could be not colored. They could be just clear. Okay, electrolytes. Also very important here. Electrolytes are soluble compounds which conduct electricity when dissolved. All soluble ionic compounds are electrolytes. Acids are also electrolytes. And that's pretty important. We've got to make sure we know which ones are the electrolytes. Okay? So that means that they conduct electricity. If you were to put a battery into them or connect them to a battery, they would conduct electrical current. Okay? And let's do this. I'll move this up here a bit. I think we're there, good there. So that's electrolytes, are soluble compounds which conduct electricity when dissolved. All soluble ionic compounds are electrolytes. Acids are also electrolytes. When an ionic compound dissolves, the plus and minus ions separate from each other. Electricity is connected from one free ion to another. And in non-electrolytes, they are soluble compounds which do not conduct electricity when dissolved. Molecular compounds are examples of this. Okay. Molecular compounds are the only non-electrolytes. Even if they're polar, they still do not conduct electricity. Okay? So remember again, non-electrolytes are molecular compounds. Okay? So make sure they do not conduct electrical current. Basically everything else does. Okay? We're going to talk about this unit. Acids, yes, very good conductors. Bases, yes. Ionic compounds, yes. To different degrees. All those to different degrees? Sure. Okay, we're going to talk about that coming up here, and that's important as well, but they do conduct electricity in some way, shape, or form. If you have a car battery, for example, what's in a car battery, a typical car battery? I'm not talking like the fancy ones or anything, just a good old-fashioned car battery. What's in it? Yeah, what kind of acid, you know? Which is actually? Yes, very dangerous because we'll talk about that. It's sulfuric acid, okay, and it's got lead plates in there. That's why it's heavy. Okay, so lead plates and sulfuric acid, very good conductors of electricity. Again, we use sulfuric acid for a reason, and we'll get to that. It might actually come up on the next page here, but we'll see. Okay, all right. Now, we're going to talk a little bit about 3 definitions, and just before you start getting crazy copying, just listen. Listen. 3 definitions, and you need to know these so that we can use the appropriate terms, okay? So the first one we're going to use is called separation, and what you have to remember about separation is it goes with molecular compounds, okay? Separation is molecular compounds. That's the first term that we're going to use, okay? And I'll let you copy here. And then there's a few diagrams we'll draw out together here. I already drew them because I don't know why. Separation is spreading out of individual molecules. It takes place when a molecular compound is dissolved in water. Make sure you underline that. Make sure you know that. So basically what they're saying here is this. If you take a molecular compound and you put it into water, okay, it's going to break apart. So for example, most of us have probably taken sugar, yes? Let me get rid of this here for a second. And of course, sugar, okay, it is, you know, even if you take, you don't even have to picture this, but even if you took 1 grain of sugar, or if you took even a cube of sugar, let's say, okay, which has been kind of compacted together, whatever you want to picture in your head, okay, and you decide you're going to take that sugar cube, or even that grain of sugar, and you're going to dump it into some water. So you're going to put it into some water. So this C12H22O11, okay, remember, it's quite a large molecule, yes? It is molecular. So this goes back to Unit 1 a little bit here. We can talk about this. What kind of forces would be involved in sugar? Well, probably it's a pretty large molecule, so obviously it's got London forces, yes? Every molecule has London forces. Probably for sure, there's probably, if you drew this out, I would think it's probably a polar molecule, because I don't think it's very symmetrical. And third, I would even venture a guess that there's probably going to be, look, there's a lot of H's, and there's quite a few O's, and there's 12 carbons, right? So I think at some point, you're probably going to have some hydrogens bonded to O's, yes? Which of course is hydrogen bonding. But remember, this sugar is combined to another sugar. If you took solid sugar, yes? Look, they're telling you basically that sugar is a molecular compound, it's in solid form. That means that those forces have to be stuck together, yes? So that hydrogen bonding is probably fairly strong, I would think, and then it makes a solid here, okay? Whether you think it's that 1 grain of sugar, even in that 1 grain of sugar, think about 1 grain of sugar on your fingertip, just that 1 grain. You know, you go to 7-Eleven, you dip your finger in, and you pull out 1 grain of sugar, right? You can't do that now, but I'm just saying, well, you couldn't do that before either, actually, but you shouldn't. But if you get 1 grain of sugar on your finger, how many molecules are in that 1 grain of sugar? Lots, yes? Right? I don't know exactly. I guess we could go weigh it and figure it out. Because we could take the mass and the molar mass and find out N. And then we could do N times Avogadro's number, and that would tell us how many moles, or how many molecules are roughly in that 1 grain, yes? Okay? So we could probably do that, but it's probably still going to be a lot, yes? Because 1 mole is 6.02 times 10 to the 23. You'd probably have maybe, you know, I don't know, 100th of a mole or something like that, probably even less than that, and probably, you know, accordingly, but whatever. You got a lot of molecules of sugar in that 1 grain. If you want to picture a cube of sugar, that's fine. You got even more molecules there, yes? And that's fine, but they're all linked together. When you put them into water, because water is polar, okay, water is polar, it's got a negative end and a positive end, it's going to basically attach themselves to these water molecules, and it's going to break those intermolecular forces, okay? What happens when you put sugar into water? You take that 1 grain, you dump it in, or you take the sugar cube and you dump it in, stir it up, what happens? It dissolves, it disappears, yes? That's because now you do not have sugars linked together, you have individual molecules of sugar, yes? Okay? And you can't see an individual molecule of sugar. If you put sugar into your coffee, okay, or into water, and then you drink it, right? It tastes like sugar, yes? You still have sugar in there. It's just that you have individual molecules of sugar. You can't see them anymore, okay? And that's what this is basically saying right here. If you take a solid chunk of sugar and dump it into some water, okay? There's the water, by the way. That's a little abbreviation we use for water. Make sure you know that, of course. That's aqueous, AQ, which we did last year, I think, as well. But regardless, that's AQ. That means into water. We get individual molecules of sugar. okay? Individual molecules which you cannot see because we don't have enough of them linked together to see them. So we get individual molecules of sugar there, okay? Again, remember, this is a molecular compound, so this would not, if we dump sugar into water, we put a conductivity tester in there, it would say 0. Okay, we do not get any electrical conductivity because molecular compound, separation, non-electrolyte. Okay, separation is the term that we said, you guys said it dissolves, right? The technical term for that is called separation. Okay, and we separate individual molecules out, basically. Okay, good. Okay, so that's separation. Next one we're going to talk about is something called dissociation. This happens for ionic compounds. So again, dissociation, ionic compounds. Those are the two terms that go together. Make sure you know that. And then there's a few examples down here, so go ahead and fill whatever you need to in there. And I'll pause it. Okay, so dissociation is the term that we want to use for ionic compounds. Anytime you're dealing with an ionic compound, we're going to call it dissociation. Okay. Basically, what that means is when we take, for example, sodium chloride, which is salt, same kind of thing happens. You dump it into some water, and water is polar. It attracts the negative end and the positive end of this ionic compound and breaks it apart. Now, there's different solubilities for ionic compounds, and those are on the back of your periodic table, which we're going to talk about in a little bit here, and we're going to review that. But remember, on the back of your periodic table, you have those 2 rows, right? Remember, there was a list of ions. It's right here, actually. Let me just find that for you real quick here. Right here. If you remember on the back of your periodic table, come on. Okay, that's not going to work. Where are we here? Well, this isn't going to work now either. Okay. Let's see. Yes. Oh, here we go. Okay. Right there. Okay. So remember this chart from Science 10 probably kind of thing, right? So again, we're going to use this coming up here, but ionic compounds will break up to some degree, okay, whatever that is. Some are very soluble, so that would be this row right here, of course. Some are what we call slightly soluble, okay, but they all break up to a certain amount, okay, and we're going to talk about that coming up in the lessons here. But this, again, okay, anyway, moving on. But if you take a sodium chloride, which we know has got ionic forces, ionic attractions, yes, plus minus, all ionic compounds are solid form when they're in, in a bottle somewhere or whatever, or in the back room. So solid form, but when you put them into water, they will break up into 2 ions, yes? And of course, this would conduct electrical current, because if you look at this, we get a positive and negative, of course, that come out of this. And positives and negatives are what conducts electrical current. Some very well, like these ones would probably be pretty good. Actually, the magnesium chloride one might not be, but I'd have to look that up. And some are kind of poor, but they always conduct electrical current to some degree. Okay. Note, ions are present in a solution. That means, therefore, solution will be able to conduct electricity. Okay, so the solution will conduct electricity. Also, included in ionic compounds are something called bases. Bases are ionic compounds that contain the hydroxide ion. You should know this. Okay, actually, you should know this from Science 10, but regardless, so we're going to tell you again here. That hydroxide ion, OH1 minus, OH minus, is a base. Whenever you see that OH minus, that means it's a base. When bases dissociate, OH minus ion is responsible for the property of bases. For example, turning litmus paper blue, having a pH higher than 7, okay, all those things. Okay, that's what makes that happen. Bases are also ionic compounds, so they also are dissociation. Okay, bases are dissociation. Because basically what we have here is barium hydroxide ionic compound. Put it into water, it splits up into barium ions and hydroxide ions. Hydroxide ions are a base, but it acts as an ionic compound, of course. Okay? So that also is dissociation. Okay? Bases are also part of dissociation. Good? Questions, anyone, for that? Okay, we're good. Okay. Now, the last one we're going to talk about, so far we've done separation, molecular, dissociation, ionic, and bases. Okay. And the one we haven't done yet is, of course, acids. Okay. Now, I'm just going to get rid of this for a second here. And I'll let you copy here, but it says most acids are molecular compounds, and therefore only neutral molecules are present. However, when acids dissolve in water, they become electrolytes. Acids separate into individual molecules and ionize into positive hydrogen ions and negative anions. And ionization is the term that we need to know for acids. Ionization is acids. In fact, I'm going to do this. Okay? And I'll let you. Now, acids are, like it says here, molecular compounds. But then they have the ability to ionize. In other words, turn into ions as well. Okay? So we needed a kind of a special term for this because it actually does both of the other two processes that we talked about. It first kind of, if you want to think of it this way, but acids kind of separate first, and then they ionize, or sorry, then they dissociate after that. And we couldn't call it separation, dissociation. We had to come up with a new term, so we called it ionization. Okay? And basically, here's how it works. Acids are molecular compounds. Okay? And I'm going to go up to this part right here, and I'm just going to show you this. If I was to draw HCl, okay, we would probably look at things like from Unit 1, something a little like this, and you can go ahead and do this because I think you got some space there. I'd probably draw it like that, yes? HCl. Because we would still call it probably hydrogen chloride. This is a gas at room temperature, by the way, hydrogen chloride. Now, this here, okay, hydrogen chloride. How do I know it's a molecular compound? How do I know to draw it like that? What do I use from Unit 1 to decide that? Do you remember? How do I know that that's a molecular compound? What would I look at to decide that? Check the what? Check where they are on the periodic table. A little bit more specific than that. Electronegativity, right? So I would look up electronegativity values. I think what chlorine is 3.2, hydrogen is 2.2. So if I subtract the two, it's about 1.0. Yes, it's definitely polar for sure, but probably not big enough to have a positive and negative ion. Okay, but it is a molecular compound, polar molecular compound, probably. The first thing it's going to do is this. When I take this hydrogen chloride gas and I put it into water, it's going to basically do this. So it's going to break up into individual molecules of hydrogen chloride. By the way, it's probably going to do that anyway because it's already a gas anyway, right? So there's a lot of empty space. The attractive forces aren't particularly strong. But the first thing it's going to do is what we call separate, okay? Molecular compound. But then water is going to start attaching itself to these H and Cl's, okay? H is going to be, of course, become this here. So this is now going to turn into that, H plus and Cl minus. It's going to break up into two ions, okay? So with acids, how do you know if you have an acid, by the way? What do you look at? How do you decide if it's an acid or not? If what? There's two things actually that'll kind of tell you if it's an acid, but I think you probably know one for sure. Yeah. Yeah, but like just like looking at the formula, how do you decide? Sorry, I should have been more clear. Yes, but how do you decide if you look at the formula? Yeah. H plus. Okay. So if H is the first letter, then it's probably an acid. Yes. So with these acids, we're going to call them ionization. Okay. So HCl gas turns into HCl water, which turns into H plus and Cl minus. Okay. This is called ionization, is the term we use for this. And again, this, and now I don't know if it's going to say this here, this, does it say, anyway, this gives me the acidic properties of acids, okay? and you might want to write that down somewhere. That H plus is what gives it, makes it an acid, okay? So again, kind of referring back to the base thing here, like we did before. In this case, acidic properties would be what? pH less than 7, yes? So if I put a pH meter into this, it would be less than 7. Acids turn what? Red, yes? So if you have blue litmus paper, it would turn red. If it was red, it would stay red, okay? Things like that. So that's responsible for the acidic properties of acids, okay? All acids make that, just like all bases make OH minus. All acids have to produce H plus ions, okay? And that's what we're going to go with for right now, anyway. Now, okay, let's just take a break here. Now, this is a super important concept coming up here, and then, well, we still got some time, so we'll see, but super important concept. Good thing you're here. But first of all, let's just do a quick little review here. Again, if we talk about separation, okay, that's not the button I wanted that one. Okay, if we talk about separation, we're talking about molecular compounds undergo separation. Dissociation is for ionic compounds and bases. Ionization is for acids. You have to know that, okay? Have to know that. That's 3 definitions that we need to know, okay? Now, when we talk about acids, and eventually we'll talk about bases in the same way, but when we talk about acids, you've probably heard these terms before. Acids can be classified as strong and weak, okay? So some acids are strong and some acids are weak. What does that mean to you? If I said, hey, today we're going to go to the lab, and we are going to play with some strong acid for fun. What would that mean to you? What do you think of automatically? Yes?
Very acidic, low in pH.
Very acidic, low in pH. What else? Be careful. What else? Damage you if you do something stupid. Yes? Very corrosive. Okay? Melt your face off. Right? Kind of thing. Yes? Okay? And I'm going to tell you that you're all wrong by definition. Okay? So this is what we need to carefully consider. Okay? It's not, can they be? Absolutely. Right, absolutely. Any acid is dangerous, by the way. Okay? When we talk about strong and weak acids, we need to get away from that thought process. Okay? When we talk about strong and weak acids, by definition, it is based on this. Okay? So, and I don't know if you need to copy this or not, I don't remember here, but strong acids will completely ionize in solution. They are very good electrical conductors. Okay? So does that make them dangerous? Yes. But having said that, there's a lot of variables that can go into this as well. So they could be very not dangerous as well. Okay? Strong acids, by definition, are how well they break up when you put them into water. Okay? So strong acids completely ionize in water. Okay? Do you need to copy something there? Okay, copy. And then I'm going to show you an example. Huh? Yeah. So again, strong acids completely ionize in solution. They are very good electrical conductors. We're not going to copy down the strong acids right now. I think we're going to give you a list of that later. So don't worry about it. If you do, that's fine. There's technically 6 strong acids by definition. Okay, there's only 6. And you might say, well, how is that possible? Like, there's a lot of different variables. Remember, it's how well they break up in water. That's the definition. There's only 6 that break up very, very well. Okay, and I'm going to give you a simple example here, which is HCl. Okay, when I take HCl gas and I put it into water, I get H plus in water and Cl minus in water. Okay, and now I'm going to give you some numbers here, basically, and I'm going to kind of show you this. Now, these are general statements, so you cannot quote me on this, but, okay, this is kind of what we say. If I took, and I'm just going to take this number because it's nice and easy and it's percentages, okay? If I took 100 of these molecules here, if I took 100 molecules of HCl, 100 molecules. Okay, you can write this down as well. If I took 100 molecules of HCl and I put them into water, okay, if I took 100 molecules of those and put them into water, what happens is those 100 molecules will convert to make 100 of these and 100 of these. In other words, those 100 will completely convert into H plus and Cl minus. And then technically, when I put these 100 in, I would get 100 of those and 100 of those, and I'd have none of those left. In other words, we say that the ionization rate here, or that conversion, is about 100%. Okay? Technically, sometimes we say it's 99, just to leave a little bit of leeway there, kind of thing. But this is basically approximately 100% ionization. Okay? That's what a strong acid means. In other words, I take 100 of these, or I take a million HCl's, I get a million H pluses and a million Cl minuses, and I'm left with nothing of the compound left over. Okay? They completely convert, and you're going to see this. Boom. Okay? This will change into that and that completely. Does that make sense? Is there any questions? Okay? That's what a strong acid does. So again, now, how do you make it more, how do you make it have a lower pH? What could you do? You could add more of these, yes? The more of these you add, the more HCl's you add, the more H pluses you get. The lower the pH will go, yes? Because H plus is the responsible part of acids, yes? Okay? Good. Okay? So we could make those, like I said, that's how we make it. We could, instead of putting a lot of water, we could use less water. Okay, we're going to talk about concentrations coming up as well. But that's what happens with the strong acid. Okay, we get a lot of H plus, we get a 1-to-1 ratio basically. So for every one of these I put in, I get one of these and one of those. That's what a strong acid is. Okay. Now, there's some, these are only 3 of the 6 strong acids. So if you don't want to, I guess, do we want to write down the rest now? Yes, no? Or just wait? No, let's just wait. Okay. Those are some of the strong acids. Okay, some of the strong acids. Weak acids only partially ionize. Partially ionize. They will not conduct electrical current as well as a strong acid will. I'll let you just copy. So, weak acids only partially ionize. In other words, they're not going to break up completely. And we're going to talk a little bit about that. They will conduct electricity, but not as well as a strong acid. So again, by the way, if we're talking about strong acids and weak acids, which one are you going to put in your car battery? Strong acid or a weak acid? Well, sulfuric acid, strong acid, yes, because it's a good conductor of electricity. Okay. Could you use a weak acid? Sure. Are you going to get the same conductive current or the same power from the battery? No. Okay. So that's why we use sulfuric acid in this case. Sulfuric acid and lead plates, a big difference in electrical potential, which you'll learn in Chem 30, which is good. That's what we want. Big difference. That's going to create a lot of electrical voltage there. Okay. So good. Here's some common weak acids. You don't have to memorize these or anything like that. By the way, again, listen, there's only 6 strong acids. Only 6 in the entire world. Everything else is weak. So if you know the 6 strong, then you know all the weak ones because everything else is weak. Okay? So here's what this looks like. Okay? By the way, okay, I'm going to tell you the second part of this now. So we talked about earlier, how do you know if you have an acid or not? Well, again, if H is in the front, like this one here, for example, HCl, okay? H in the front usually tells you basically, and this is H plus, of course, and this would be a Cl minus technically. That would be an acid, yes? H plus and Cl minus. That would be an acid. The other thing that you want to look for is this kind of common thing here. So you'll notice H in the front, yes? H in the front, or this grouping of atoms here, COOH. Okay, COOH is another way to tell that you have an acid. Okay? COOH. And technically, by the way, in this, well, and I'm going to erase that for a second here, but in this one here, CH3COOH, this is actually the H plus right there, and then this is the minus part there, if that makes sense. Okay? But it's grouped together as COOH. It's called a carboxylic acid. Again, that's a next year thing. Okay? So different kinds of carboxylic acids. Okay? Good? Okay? So that's the other way you're going to tell if it's an acid. I'm going to show you the exact same thing that I did with HCl, but I'm going to do this on a different level now. When we talk about weak acids, okay, it says here that they only partially ionize. So what does that mean? Well, okay, if I take my CH3COOH here, I think that's a liquid, but I'm not sure, and I put it into water, I am going to get this, basically. CH3COO1 minus and H plus. So I'm going to get this. Okay. However, there's a few little adjustments we're going to do here as we go through this, and then we're almost done here, and we'll actually wrap it up after this. But the same situation, because this is a weak acid, if I take 100 of these, okay, and again, I'm just using 100 because of percentages. Okay? And now I'm going to tell you that this is a lie, 100%. Next year, you're going to get a data booklet that's going to tell you this ratio, okay? And you're going to figure that out based on that. But for Chem 20, we're not getting into that, okay? I'm going to tell you this. If I took 100 of these and I put them into water, I do not get 100 of these and I do not get 100 of these because that would be a strong acid. In this case, I get about, and this is the part I'm lying to you, about 1. So for every 100 I put in, I get about 1 of those ions. And what that means is 99 are still stuck together as CH3COOH. Okay? Does that make sense? So like 99 of them stick together, 1 of those compounds will break up. Okay? We call this an equilibrium as well. So not only do those 99 stick together and 1 break up, but that one that you might say, well, how do I know which one breaks up? Pick one. Okay? That one that broke up, though, is going to get back together at some point, okay, and make another molecule. So what we're going to do here is we're going to use a double arrow. Okay? So make sure you put a double arrow in there. And when you see this, you're going to know that it's a weak, in this case, a weak acid. It's what we call an equilibrium. Okay? And again, I'm lying to you, it's not 1%, basically. It's not one of them. It's actually less than that. In this case, I believe, if I'm not mistaken, it's like actually 0.424%. Okay? It's not a lot. Okay? However, that's what we're going to go with this year. Okay? So that's what a weak acid does. Most of them stick together. Only about 1 break up. Okay? Again, which one's going to give you, look, what's the best bang for your buck if you're going to use a battery? Are you going to use this, where you're going to have 100 and 100, lots of positives and negatives? Or are you going to use this one where you get 1 and 1, right? Probably 100 and 100, yes? I mean, that's your better ratio there. You're going to be getting a lot of ions, a lot of conductivity. This one, you get a little bit of conductivity, right? Okay? Now, obviously, that depends on concentrations, how much you use, et cetera, et cetera. Again, we need to get away from the thought that strong acids are super dangerous. Acids are dangerous in general, okay? Acids are dangerous in general. So are bases. That's fine. But a strong acid is just how much it breaks up in water. That's the only thing that's what determines a strong acid. And there's 6 of them, okay? Everything else doesn't break up as well, and therefore we call them weak acids, and that's all it's based on. This weak acid, I could make this weak acid have a pH of 1. Okay? It's not hard. In fact, we probably have some that has a pH of 1. Okay? I could make a strong acid have a pH of like 6.9. Basically, you could probably, I don't want to say this, but you could probably drink it and you probably wouldn't even notice. Okay? It really wouldn't matter. So it's not based on pH or how much it's going to melt your face off or how corrosive it is or how, you know, all this other stuff. It is just based on the definition of how much they break up when you put them into water. Okay? Yes, pH is a factor. Yes, concentrations are a factor. Those are all things that we can consider in the big scheme of things for like how dangerous would that be to us. But as far as strong and weak acids, that's their definition. Okay? And we'll leave it at that for today.